Hello everybody. Good afternoon. Welcome to this interactive session on aircraft design. First, I would like to summarize what sir has discussed in this previous 1 week. Okay, and then we will solve a few questions. Okay, if you have any doubts in between, you can ask me. I will you can ask me in between. I will try to answer them. So, in the first week, basically, sir talked about aircraft design, introduction to aircraft design, and I think that he did not teach anything in detail, but he discussed what kind of, and he discussed a few examples and what kind of problems and what is the design process. Okay, so he discussed many things about some conflicts and trade-offs in the design process. He discussed briefly about wing loading and thrust loading, which are very important parameters for aircraft design. Then he also briefly discussed about selecting the CL, CL by CD and the cruise velocity. He also discussed a little bit about selection of the aerofoil and also range and endurance of the aircraft and estimating the weight of the aircraft. So we will discuss these topics for some time. So first what is the question comes is that what is aircraft design? So aircraft design is the process of conceiving, specifying, creating the configuration and basic features of the aircraft. So you can understand from the term aircraft and design. So it means to create, to design an aircraft. So this is different from the previous courses that you have done, which is aircraft performance or aircraft stability. In those cases, what happens is that you are given a aircraft. So you are given an aircraft and you have to find out its properties. Properties such as range, then endurance, all this. Okay. But aircraft design is kind of like the opposite process. Okay, you are given the required properties, so I would say required properties, and you have to find a aircraft. You have to come up with a aircraft configuration which satisfies these properties. So suppose somebody tells you that I need a aircraft which can fly from which can fly at so and so velocity, which can fly at supersonic velocity. So what kind of wing will it have? What it will be the size of the aircraft? So these kinds of questions. So some kinds of questions which are covered here are: what is the size and weight of the aircraft? Okay, so will it be a small aircraft or a big one? So obviously, if you have to carry a lot of passengers or a lot of cargo, then you need a very large aircraft, and the weight will also be large. If you require a highly maneuverable military aircraft, then the size and the weight has to be lesser. Then how many and what kind of engines will it have? This is also a crucial question. Okay, so will it have one, two, three, and will it have a propeller engine or a jet engine? So these kinds of questions. If you have for the long range airliners, they are required to have multiple engines, because if one engine fails, it can still fly on the other engines. So these kinds of requirements, the requirement of flying for a long range, it dictates the number of engines. So this is part of the design process. Then what is the wingspan? So what is the size and shape of the wing? What is the aerofoil, will it be swept back or not, and then how many degrees will it be swept back, and then what is the cruising speed of the aircraft. So will it like small propeller planes like Cessna and all, they cruise at a low velocity, whereas your normal civilian aircraft, they cruise at high velocities like close to Mach 0.78, point 0.8. Okay, you also have one aircraft, the Concorde, okay, which is a passenger aircraft which used to cruise above Mach 1. So the cruising speed also dictates the size, weight, engine type, the uh, wing design, all these things. So this is a kind of example problem which will be, this is a kind of problem which we'll try to address in this course. So you can see that the problem states that two-seater fighter aircraft is ordered to be designed to fulfill a military mission and meets the following mission requirements. So you can see that the properties of the aircraft have been given, and we have to determine the optimum configuration of the aircraft. So uh, so you can see that this is maximum speed is Mach 1.8 at 30,000 feet. So immediately you can see that it is a supersonic aircraft. So it will have, like, we'll have to design the wings in such a way that it can fly efficiently at that speed. Then the absolute ceiling is higher than 50,000 feet. So no, your normal civilian aircrafts, they fly at 30,000 feet. So this will require better engines to go to that altitude. Then we have radius of action and rate of climb, takeoff, run. So all these properties are given, and we have to answer these kinds of questions like size, weight, wingspan, engine. So once we answer all of this, we'll have a basic aircraft configuration which we can then optimize. So the process is kind of like this. So we are given the aircraft design requirements such as which was covered in the previous slide, and then from there we try to identify major components that the aircraft requires to satisfy the mission design. Okay, so the major components are the wing configuration, tail configuration, then engine, landing gear, structural and mechanisms. Okay, so like for example, so this wing is there. So will this wing be situated below the fuselage or above the fuselage? Okay, what will be the wing incidence angle? So these kinds of things we decide. Then tail configuration. So how much of the tail will be elevated and how much of it will be how much of the vertical tail will be rudder. Okay, how far back will the tail be? So these things we answer. So then we come up with a approximate aircraft which satisfies these requirements. Okay, and for this process we may use historical data also, or historical or statistical data also, and then once we come up with this approximate aircraft we can then optimize it. Okay, so in one, like, we'll see that aircraft design is a, like, there oftentimes there are conflicting requirements and conflicting trade-offs, and we cannot optimize everything. Okay, like if we want it to go faster, then the engine size will also increase. So we cannot both keep a smaller engine and a higher velocity. So all these trade-offs happen in the aircraft design process. So it is actually not really this kind of a linear process. It is more like a iterative process. So we design it like this, but then some things may have to be tweaked, and when they are changed, it affects other parts of the aircraft also. Then we have to go back. So like it comes like this, but then we might see that when we are optimizing something, it changes other aspects of the aircraft, and then we'll have to again go back to the first step and then again optimize it. Okay, so we have to keep doing this until um, the properties that we care about, they are sufficiently optimized. Like in some aircraft we might optimize for range, like they have to go for a long distance. So in those cases we might uh, we'll give more priority to the range. Okay, but in some cases, some aircrafts we might give more priority to maneuverability. So depending on what is required, we'll give priority to that property. So often there are conflicts in the design process, and not everything can be optimized. In that case, some aspects are given more priority over others. Wait a minute. So, like as I discussed, so a stronger structure. So there are some examples. Okay, stronger structure increases the weight, which requires a bigger engine. So it is difficult to have a stronger structure and a low weight, or a stronger structure and a smaller engine. So again, another thing is a higher cruise velocity increases drag, which might require a bigger engine, or cruising at high altitude. So again, like we cannot both like cruise at high velocity and have a lower and have a smaller engine, and also it is difficult to cruise at high velocity at a low altitude because the drag is a lot. So okay, there is a usually a trade-off between your altitude and velocity. Okay, so if your so altitude determines the air density. So if your air density is low, then we can cruise at high velocity. Whereas if the air density is high, we have to cruise at lower velocity. But this relationship is only true up to a point because the aircraft engines also require the air. Okay, so if we cruise at very low air density, then there isn't enough air to make the engines function. Okay, but in the range like we are considering, this relationship is true. Like in the troposphere, this relationship is true. Another thing is that both range and endurance of the aircraft cannot be optimized. Like we cannot have an aircraft that has maximum possible range and maximum possible endurance. Okay, it might have maximum range and a slightly lower endurance, or maximum endurance and slightly lower range. Then another example is that when we try to choose airfoil, we try to maximize the lift coefficient. Okay, so that like a smaller wing can generate the required lift. But so for that reason, usually we choose cambered airfoil. So a cambered airfoil increases the lift, but it also increases the pitch down moment. So pitch down moment, it makes the aircraft unstable. So you can see that during the selection of the airfoil, there is a trade-off between the lift and the stability. So we might have higher lift, but the stability might go down. So these are some examples of some conflicts. Now I'll discuss wing loading. So like as you know that when the aircraft goes, like in cruising condition, these are the forces acting on the aircraft. So the four primary forces are the lift, the weight, the drag, and the thrust. Okay. So we have lift equal to weight and thrust equal to drag at cruise condition. Now we'll take the first equation, okay, lift equal to weight, and the lift can be expressed as half rho v square s cl equal to weight. Okay, so from this we can find out the velocity. It is cruising, and it comes out like as this 2 w by s rho cl. So we can see that the velocity, the cruise velocity, and the cruise velocity is like in an aircraft, all the velocities are kind of interlinked. Okay, so if your cruise velocity is higher, your takeoff velocity, stall velocity, everything is going to be higher. Okay, if your cruise velocity is lower, everything, all the other velocities are also going to be lower. So you can see that the cruise velocity depends on uh, the weight, the wing surface area, the density, and the CL. Okay, this quantity W by S, it is known as the wing loading. Okay, this is known as the wing loading. And this wing loading factor, it affects uh, a lot of the wing loading factor. It affects many things in the aircraft, but primarily the velocity. Okay, the velocity the aircraft is flying at. So wing loading is the quantity W by S. It affects every aspect of the velocity of the aircraft, such as stall speed, takeoff speed, landing speed, and cruise speed. Okay, so from this, from the formula, like during stall, takeoff, and landing, your CL is CL max. Okay, but the rest of the quantities are same, right? And during cruise, your CL is going to be lower than CL max, but the rest of the quantities are going to be similar. So uh, the quantity W by S, or the wing loading, it affects the all the velocities, basically the stall speed, takeoff speed, landing speed, cruise speed. Okay, so then the so this is the direct effect of wing loading, but it has indirect effects too, because higher velocity will require a heavier engine, or it will require a more powerful engine, which is usually heavier. Okay, so it will require a heavier engine to move at higher velocity. Okay, and another indirect effect is that higher wing loading requires a stronger structure. Why? Because wing loading is W by S. So if your weight is fixed, okay, if your weight is fixed and you want a higher wing loading, then your S is going to go down, which means the wing area is going down. Okay, so a smaller wing has to lift a lift the same weight. Okay, so earlier, if your plane was like this, okay, if your wing loading goes up, okay, then your the same weight has to be sustained by smaller wings. So this will require a stronger structure, because uh, the wings the wings have to be stronger, and both these things might in turn increase the weight of the aircraft. Okay, so this was the primary effect, and this was the primary effect, and these were the secondary effects. Okay, but both these effects, they might increase the weight of the aircraft, and when the weight increases, your wing loading will again change. So then you will have to, because the weight is there in the wing loading, right? So your weight will again change, and you will have to again perform this optimization process. So as I said, this is a iterative process. Designing is a iterative process. The next quantity is the thrust loading. So, so in this case, again we'll have the component forces acting on the aircraft. Okay, so in this case, I have drawn the aircraft as it is climbing. So in a steady climb, so this is a steady climb. So in a steady climb, we have thrust minus drag minus weight sine gamma equal to 0. Okay, and then we can divide by weight and rearrange to get this. Okay, now this quantity, your T by W, it basically tells you the amount of thrust required for the depending like as a proportion of the weight of the aircraft. Okay, and this this require this so this quantity T by W, it will affect which engine you choose, how fast you can go, like what is your cruising velocity. It will also determine your climb rate. Okay, now one thing you can see is that your T by W, it depends on the climb angle and the CL by CD. So during cruise, your gamma is 0, which means that T by W is 1 by CL by CD. Okay, but during climb, your CL by CD is usually higher than 10, 15. Okay, so CL by CD's contribution is approximately 0.1. So like 1 by CL CD. So this is approximately equal to, okay, so this is during climb. So during climb, your T by W is mostly determined by your climb angle, and during cruise, your T by W is mostly determined by CL by CD. So thrust loading is the quantity T by W, and thrust loading is much higher for climb than for cruise, and thrust loading is also higher during takeoff. Higher thrust loading results in faster cruise velocity, steeper climb, tighter turns, and shorter takeoff distance. So you have seen that your fighter aircrafts, like they can go very fast. Okay, they can go very fast. They can climb very fast. They can take very tight turns. Okay, and they also require a shorter runway for takeoff. Whereas you can see that the passenger aircrafts we travel in, okay, they they have a lower T by W. So the fighter aircrafts, they have high TW, whereas the our passenger aircrafts, they have a low T by W. So they are more sluggish basically. The fighter aircrafts are more maneuverable, whereas the passenger aircrafts are more sluggish. So the passenger aircraft, they cruise at lower velocity. They cannot climb as fast as the fighter aircrafts. They cannot take tighter turns, and they require a longer runway for taking off. So a higher thrust loading requires a heavier engine, which again increases the weight. Now one important note is that, yeah, both the quantities thrust and the weight, they change throughout the flight. Okay, so as the aircraft is flying, it the fuel will be consumed, which will reduce the weight. Okay, and similarly, uh, as the aircraft is flying through various altitudes, uh, depending on the air pressure, the thrust produced by the engine might also change. So if we want to compare T by W at various phases of the flight, uh, for proper comparison, we have to convert the quantities back to takeoff. Okay, so like for comparing, for comparing T by W at various phases of the flight, both the thrust and the weight have to be converted back to sea level takeoff condition. So all these things they will be discussed in detail in future lectures. Okay, so in this week just the introduction was done. Next we have selecting the CL and the V cruise. Okay, so CL what CL must the aircraft fly at and what should be the cruising velocity. So this depends on whether we are optimizing for range or endurance or maybe some other factor. Okay, like maybe the fighter aircrafts, they don't have to worry about range because they're going to fight in a smaller area, right? So they might worry more about endurance, like staying up in the air for a longer time. Okay, or they might not worry about range or endurance, they might worry about maneuverability. Whereas your long distance passenger aircrafts, they worry about, like they optimize about for range. Like there are some aircrafts in the world right now which can almost cross the entire world. Okay, so yeah, you might have heard about some flights which are like 22-hour flights. Okay, 20-hour flights. So they might go from. Actually, recently I heard about one flight which takes up somewhere in USA and it lands in Singapore. So this flight almost crosses the entire Earth. Okay, so for designing this aircraft, range has to be optimized. So that will again dictate the CL and the VC. Okay. So you usually, so like although it depends on these factors, but usually we fly close to CL by CD max. Okay. And this decides the CL. Okay. So another table is there. Okay. Let me write down the table. So sir has discussed this in class. So jet engine, prop engine, and then we have range and endurance. So this table tells you at what fraction of CL by CD max should you fly at to optimize for range or endurance. Okay, like for example, if you have a jet aircraft and you are optimizing for range, then you have to fly at 86% of the CL by CD max. Okay, but if you are optimizing for endurance, then you have to fly at CL by CD max. Okay, but you can see that still it is almost close, right? Like for one case you are flying at CL by CD max, the for the other case you are flying at like 86%, so actually 87%, so almost close to CL by CD max only. So that is why I wrote that usually we fly close to CL by CD max, and this decides the CL. Okay, and now we come to the V cruise. Okay, so as I said that usually for civilian aircraft in troposphere, you can consider that there is a like the dynamic pressure has to be constant. Okay, so usually there is a trade-off between the air density and velocity. So if your air density is lower, your velocity will be higher, which means, and you know that air density is negatively correlated with altitude. So if you want a higher velocity, you have to fly at a higher altitude. Okay, and if you want to fly at slower velocity, you have to fly at lower altitude. Okay, another thing is that you also have to consider where the plane is taking off from or landing. Okay, because your takeoff and landing airport, if it is situated at higher altitude, then the takeoff and landing distance and the velocities they will be higher. Okay, so usually there is a trade-off between VC and rho, and we must decide VC on other factors such as cruising altitude and engine configuration. So regardless of this, okay, if we want to go at higher velocities, we have to require bigger engines. Okay, and also if you go very high, then you have to pressurize the cabin. Okay, so that might add additional weight and complexity. So depending on these things, we have to decide the cruising velocity. So one more thing that sir discussed was the selection of aerofoil. So when we select a aerofoil, we usually try to maximize the lift generated. Okay, so that with a smaller wing, okay, we can uh, lift the whole aircraft. Okay, so it has been seen that the cambered airfoils they generate more lift compared to symmetric ones. So as you know that airfoils are of two types. One is symmetric and unsymmetric. So a symmetric aircraft airfoil, it uh, both sides of the, so it is symmetric basically. Okay, the top part and the bottom part they're same. Whereas you also have unsymmetric airfoils which are also called cambered airfoils. So in that case, it might be like this. Okay, so in this case, you can see that it is not symmetric. It is the front part of the airfoil is kind of tilted up, okay, above the mean line, and also the tip of the airfoil is angled down. The tip is angled down. So this is known as a cambered airfoil, or you can say like technically positively cambered airfoil. You can also have this down, okay. You can have like this, okay, but this is not really very helpful in practice, so this is not usually used. This will be your negatively cambered airfoil. Another kind of airfoil which is sometimes used, okay, there is another airfoil which is sometimes used. It is a reflex airfoil. So it is like a cambered airfoil, but just at the tip it is angled up. Okay, so it's like this. Okay, so like a cambered airfoil, it slopes down, but right at the tip it again slopes up. Okay, this is a reflex airfoil. So usually your cambered airfoils, they generate positively cambered airfoils, they generate more lift than all these other airfoils. So we try to use cambered airfoils, but cambered airfoils also induce a unwanted pitch down moment. Okay, so cambered airfoils have CMAC less than 0. and they also have a lower stall. Okay, lower alpha stall, so lower angle of attack. Like we can fly them at a lower, we have to fly them at a lower angle of attack. So now you can understand that why this happens, because see over here the air will flow like this, right? It will flow like this. But in this cambered airfoil, the air is kind of pushed downwards. Okay. So when the air is pushed downwards because of the tip, okay, when the air is pushed downwards, it will produce a reaction force, which it will produce more reaction force, which pushes it upwards. But since it is being pushed downward from the back, okay, there will be more force over here, which will cause a pitch down moment. The opposite thing happens for negatively cambered airfoil. So here the air is pushed upwards. Okay, so that is why there will be more downward force. Okay, so this is actually worse than symmetric airfoils. And in this case, there will be a pitch up moment and a reflex airfoil. So if we use cambered airfoil in a plane, we have to this configuration is actually unstable because it produces a pitch down moment. So to compensate, we need a tail. Okay, so in stability and control, you must have read that we need a tail at the back which stabilizes the aircraft. But if we want to, if we don't want to have the tail, okay, there are some aircrafts which do not have a tail. They are called as flying wing configuration. So you must have seen some military aircraft which look like this. Okay, so there is just a wing. Okay, the cockpit is situated here. Okay, there are engines here, but there is no tail. So in those cases, we use a reflex airfoil, because the reflex airfoil, it because of the small tilt at the back, this because of the small tilt at the back, the air is pushed up, which produces a pitch up moment, which makes it stable. Okay, or at least stable, more stable than cambered airfoils. So these considerations are there. Then another consideration is your drag bucket. So usually we observe that the if we plot CD by CL, usually there is a relationship like this. Okay, so wait, wait. Usually there is a relationship like this. So there is a region there is a region of CL where the drag does not change much, and we would like to fly in this region. Okay, we would like to operate in this region, and we would like this region to be as big as possible. Okay, or at least sufficiently big. Okay, if we just optimize for lift, then these other things, they might suffer. Okay, we might have an unnecessary high CMAC, we might have a lower alpha stall, and we might have a smaller drag bucket. So when selecting aerofoil, although we maximize the lift, but we also have to pay attention to CMAC, alpha stall, and the drag bucket. Next, sir has also discussed about selecting the weight of the aircraft. Like not really like selecting, or you can say estimating. So you can say estimating the weight of the aircraft. Okay. Now, of course, like it will depend on how big the aircraft is. Okay. So uh, I think like if we have a good idea about the size of the aircraft, then we can get a estimate of the weight of the how big, how heavy is it going to be. So we can break down the total weight into its components such as crew, payload, fuel, and the empty weight. So WF is your fuel. Okay. Now for crew and payload weight, okay, we can get those weights from the requirements itself, because your requirements will have something like this. Okay, the plane must carry 50 passengers. So you might have a requirement like this. So from there you can like if you know that a average person weighs like 70 kilos, so then you can multiply it and get an idea about the weight of the crew. Okay. Your requirement might also have that the plane has to carry 1 ton of cargo. So from that you can get a idea about the crew and payload weight. Okay, the rest of the things like the fuel weight and the weight of the empty aircraft, those have to be estimated from the design process. Okay, like while designing we'll have to estimate it, or we'll have to use historical or statistical data. Okay, now one thing you can see is that if your aircraft is has to fly for a very long range, then it will require uh, more fuel, right? So then your fuel might be higher. Yeah, and if your aircraft is heavier, then also it will require more fuel to take up all that weight. So these considerations are there. So we can express the fuel weight and the empty weight as ratios. Okay, so we simply multiply and divide by W naught to get these kinds of ratios. Uh, Now, why we have done this is because the the historical the historical data that is available, it is available in this form. So we have the fuel fraction and the empty weight fraction and the weight. Okay, so these things are given in the historical data. So that is why we have expressed them as ratios. Okay, so that concludes the summary. Now I will move on to some exercises. So the first question is this. Okay, with the increase in height, the density and temperature, like what happens to them? And this I'm talking about this in the troposphere only. So if you want to, you can write your answers in the chat box. Okay, so all of you are right. Okay, so this decreases. So with the increase in height and density, the temperature it decreases. I would like to take you to wait, hmm. I'd like to take you to this Introduction to Flight by John Anderson. So over there you can go to the Standard Atmosphere chapter. So this is how temperature varies in the atmosphere. Okay, so Standard atmosphere is the atmosphere model that has been constructed. So according to this, the temperature varies like this. Okay, so the vertical axis is your altitude and the horizontal axis is your temperature. So as we are rising, there are isothermal layers. So in the isothermal layers, the temperature is constant. So this is isothermal layer. So from 11 to 25 kilometers is isothermal layer. Then from 47 to 53 kilometers is another isothermal layer. So these layers are there. Then you also have gradient layers. So in the gradient layers, the temperature varies approximately linearly. So the temperature, it does not always decrease. So in till 11 kilometers it decreases, but then again from 25 kilometers it again increases. Then 53 to 79 kilometers it decreases. So this is what goes on. But when we are talking about the civilian aircrafts, we are restricted to this troposphere only, so below 11 kilometers. So in that case, we are in a gradient layer and the temperature is decreasing. Now we can find the other quantities which are pressure and density based on the temperature. So for the you can see for the gradient region, we can find pressure as this quantity. Okay, so P by P1 equal to T by T1 to the power this. Okay, now the whatever is there in the exponent, it is a constant. Okay, so this is a constant. So basically the pressure and the temperature, they are correlated. So they are directly proportional. So if your temperature decreases, your pressure will also decrease. And similarly, if your excuse me, I have a call. Like, yes, okay. So so the pressure and temperature, they are directly proportional. And similarly, the density also, you can see that this is the formula for the density, and the exponent is constant. Okay, the exponent is constant, so the density and the temperature, they are directly proportional. So in your troposphere, as we go up, the temperature decreases, so both the pressure and the density, they also decrease. Okay, now we'll move to the second question. Okay, this is the second question. Uh, you guys might like try to solve it, okay, and write in the chat box. Okay, so first, like, let us discuss the vertical tail. So as we know that the at the tail of the aircraft, okay, so this is your, like, we look at the back of the aircraft, this is your vertical tail, and if we look at it from above, then so this might be your vertical tail. Now, obviously, like, we don't want the tail to produce any sideways forces, okay. So you can see that the tail has been attached like this along the plane of symmetry. So we do not want the tail to produce any sideways forces. If it produces any unnecessary sideways forces, then what will happen is that it will cause a yawing motion. Okay, unnecessary yawing motion. So that is why the at least the vertical tail, it is always symmetrical. Okay, because like, let us say that we had put a cambered airfoil, then even at zero rudder, okay, even if we put zero rudder, it will produce force in one direction. So like, that is an unnecessary force. Like, then we'll have to find other ways to cancel out that force. Okay, we might have to attach the wing at a non-zero angle, or we might have to put some other mechanism to compensate. So like, why like complicate things? So the vertical tail is always symmetrical so that it does not produce any sideways forces. So as for the horizontal tail, so if we have the horizontal tail here, so what happens is that because of the downwash of the wing, okay, so we have a wing over here. So because of the downwash of the wing, this horizontal tail, okay, it effectively has a positive angle of attack. Okay, Like if you zoom in on the wing, okay, although the wing is straight, but the wind direction is downwards. Okay, so this kind of produces a positive angle of attack. Okay, and also the main reason is that the horizontal tail, its purpose is not to produce lift. Okay, so its purpose is to stabilize the aircraft. And also what we have is that both the horizontal and the vertical tail, they have control surfaces, elevators and rudders, which can temporarily change the lifting properties of these tails. Okay, so for I think like for the horizontal tail, we can have other aerofoils, but they're usually not required. Okay, so usually like a horizontal tail, we choose symmetric only, because it is usually not required to have a positive or negative or a reflex airfoil, because its purpose is not to produce lift. So like it will unnecessarily complicate things. So here the answer is this, symmetrical. This is the next question. Okay, so yes, like you're right. So it will affect both the stall speed and the climb rate. So like we can first try to understand it intuitively, okay, and then we can discuss the formulas also. So let us think that about higher wing loading. So we have higher wing loading. So this means that the same weight, is being supported by smaller wings. The same weight is being supported by smaller wings. So because so if your W by S is going up, okay, and here I'm considering that the weight will be same, because like we have to compare things, right? So your weight is same, your W by S is going up, so your S is going down. Okay, so this means that when your surface area is low and your other other aspects of the wing are same, then your cruising velocity will increase. Okay, we have to go faster through the air to produce the same lift. Okay, so when your cruising velocity increases, everything increases. Like as I discussed, if your cruising velocity is high, all the velocities are also high. So your stall speed also increases. Okay, now now coming to, so this part is clear. Okay, so if your wing loading is increasing, then your stall speed will increase. And usually we want a as low stall speed as possible. Okay, then because if your stall speed is low, then the aircraft is more safer because it can fly at smaller velocities also. It can it will require less runway for takeoff. Okay, it can land more slowly. Okay, so these things are there. And now coming to climb rate, so climb rate is also like ultimately climb rate is also a velocity. So if you remember, then your climb rate is your rate of climb. Okay, sorry. The rate of climb is your V. I think V sine gamma, something like, yes, V sine gamma. So it is the vertical component of your aircraft velocity. Okay, so if your aircraft is going up like this, then like if we divide it into components. Okay, so this is your horizontal component, this is your vertical component. Then this vertical component is your rate of climb. So your rate of climb depends on what velocity you are going. And when your v cruise increases, every all the other velocities also increase. Okay, so ultimately your rate of climb will also be affected. Now if you look at it in another way, then now let us look at the formulas. Okay, so so basically, see, if your wing area is going down, then we'll have to fly at a higher velocity, right? So then when we are climbing, if we want to climb at the same angle, we'll have to climb faster. Now coming to the formulas. Okay, so we know that your v cruise is equal to root over 2 w by s. So if all the other quantities are same, okay, like if you are flying at constant altitude and same coefficient of lift, then if your w by s is higher, then your vc is also higher. Okay, so this is clear from the formula. Now for the climb rate, we know that your climb rate is equal to excess power by weight, and your excess power is your power available minus power required for level flight by weight. Okay, now if your w by s, like your if you fix the engine, then your pa is fixed. Okay, and your w is also fixed. And if we uh, if we fly at higher w by s, higher wing loading, then we have to fly at higher velocity, so which will require more power. Okay, so your excess power will decrease. So that is how the wing loading will affect the climb rate also. So the wing loading will affect both the stall speed and the climb rate. Okay, so this is the next question. This is a numerical question, so you can try to solve it. Okay, you are right. The answer is 18.27 meters per second. So for this, we'll use the simple formula that we have been using. Okay, so V stall is equal to root over 2W by S rho CL max. So we can simply substitute all the required things. Okay, one thing we have to note here is that the wing loading has been given in kg per meter square, but we have to convert it into newtons per meter square. Okay, so that the units are all proper. So for that we have to multiply. So the weight will actually be W by S is actually 50 into G. Okay, 50 into G, which is 50 into 9.81. So we can calculate V stall as 2 into 50 into 9.81 by 1.225 into 2.4. So let me, so this comes out to 18.227 meters per second. Okay, so now let's move to the next question. So this is the next question. Okay, you all are correct. So the answer is 7.9. So we know the formula for drag polar, which is CD equal to CD naught plus KCL square. So by comparing with the given drag polar equation, we can say that CD naught is equal to 0.05 and your K is equal to 0.08. Okay. Now from your aircraft performance, we know that when CL by CD is max, then CL equal to square root of CD naught by K. So here we know the values, so we can find it out. So so this comes out to 0.79 Okay, 0.79. And then we can find a plug this CL value into CD to get the CD, which is 0.0999. So you can say that this is 0.1. So your CL by CD, CL by CD will be 0.79 by 0.1, which is 7.9. Okay, now the next question. Okay, yes, the answer is A in this case. So let us discuss all the things. So first, let us discuss this graph. So the D graph. Wait. So first, let us discuss the D graph. So here we can see that CL is not changing with alpha at all. So even though the angle of attack is increasing or decreasing, your CL is not changing. So this is probably like not even a wing also. This is probably something like a sphere. So because you know a sphere is symmetrical, so it doesn't matter how it's oriented, it is going to have the same aerodynamic properties. So this is probably a graph of a sphere or something like that. Maybe cylinder, it could be a cylinder. Okay. Now let us discuss the graph B. So in the graph B, we can see that at zero angle of attack, your CL is zero, and as the angle of attack is increasing, CL is increasing up to a point. Okay, so this is a symmetric airfoil. So when you have a symmetric airfoil, the airflow is symmetric on both sides, both above and below. The airflow is symmetric. Okay, so like at zero angle of attack. So when your alpha is equal to zero, then the airflow is symmetric on both sides of the airfoil. So the airfoil does not produce any lift. So therefore this CL is 0. And then when your alpha increases, okay, so when your alpha increases, suppose the wind is coming from this direction, if your alpha increases, then the airfoil produces lift. So in this region, you can see that as alpha is increasing, your CL is also increasing. Okay, CL is increasing. And we know that all wings, like whatever the wing it is, the CL increases up to a point, and then after that, even if we increase alpha, the CL drops. Okay, so the CL falls down. So this is a graph of a symmetric airfoil. And now this is probably the graph of a negative. This is probably the graph of a negatively cambered airfoil. So a negatively cambered airfoil will have a slight upward bend, okay, in its wing like this. Okay, so at zero angle of attack, the air will be pushed upward, okay, which will produce a downward force. Okay, uh, so at alpha equal to zero also, this will produce a downward force. and hence you can see that at alpha equal to 0 the Cl is negative. Okay, but like all airfoils, okay, when you increase the alpha, the Cl also increases up to a point, and after that it falls down, the Cl falls. So this is the graph of a negatively cambered. And finally the your A graph, okay, this is the graph of a positively cambered airfoil. So a positively cambered airfoil has a slight bend downwards towards the end, okay, so because of which the air goes downwards, okay, towards the end. So even at zero angle of attack, this produces a lift. So even at zero angle of attack, this produces a lift. So you can see here that at zero angle of attack also it produces a lift, and again it the Cl increases, and then after the alpha stall it drops. So since the question asks that which one has a aircraft wing has a positively cambered airfoil, so the correct answer will be A. Okay, now this is the next question. You're right. The with positive camber in the airfoil, your alpha stall it decreases. Okay, so for a symmetric airfoil, your Cl versus alpha graph is like this, and as you camber it, okay, the graph moves upward and also leftward. Okay, so the graph moves upward and it also moves leftward. So as you camber it more and more, the alpha stall it decreases. The Cl also increases. Okay, so wait, so this is actually incorrect. It will be something like this. Okay, so the Cl also increases and the alpha stall decreases. This is the next question. Okay, so in this case, the answer is this one. Okay, the last one. So here you have to understand something. Okay, so what is fixed wing UAV, what is quad rotor, and how they work. So your fixed wing UAV, it is like this. Okay, so it is a plane basically. You have your wings, you have the horizontal tail, and you have the landing gears. Okay, so how does a fixed wing UAV fly? So then you also have an engine. So the engine, it pushes air backwards. Okay, and this produces a forward force. Okay, in the aircraft. So the engine pushes air backward, which produces a forward thrust, okay, in the aircraft. So this causes the aircraft to move through the air. So when it moves through the the air moves air moves over the wings. Okay, so when the aircraft moves through the air, the air moves over the wings, and then the wings produce lift. Okay, the wings produce lift, which makes the aircraft fly. So again, uh, if you draw the force equations, this is your thrust, lift, weight, and this is your drag. So the wings also, the airflow also causes drag, as you know. So you can see that the thrust is equal to drag and your lift is equal to weight. And if you equate and rearrange the equations, then you get thrust is equal to weight by CL by CD. Okay, so uh, okay, wait. So you can write it like this. The thrust, your T by W is 1 by CL by CD. So one thing you must understand here is that in the fixed wing UAV, the engine does not lift the aircraft. Okay, so the engine is not lifting the aircraft. You can see that the engine makes it move through the air. Okay, so the engine makes it move through the air, but the wings make it lift. Okay, so then you can see from the equation that your thrust by weight is equal to this, and CL by CD is usually CL by CD is usually greater than 10, so your T by W is less than zero point 0.1. So if your aircraft weighs 100 kg, okay, if your engine can produce only 10 kg thrust, it can lift the aircraft. Okay, so even if your even if your engine produces 10 kg of thrust, it can lift a 100 kg aircraft. So therefore, in case of fixed wing UAV, your T by W is less than 1. So these are the options which satisfy the thing. And now we come to quad rotor. So in case of quad rotor, we have this is a top view, that was a side view. So we have these propellers which produce thrust, which lift up the aircraft. If we look at the side view, okay, so a quadrotor has these propellers which produce thrust, which lift up the weight of the aircraft. So a quadrotor can actually hover in one place also. So you can see that fixed wing UAV, it cannot hover in one place. It has to keep moving through the air so that lift is produced. Okay, but a quadrotor can hover in one place also. So because it can hover in one place, okay, so we may not have a horizontal force equation like this. So here we have a horizontal equation also, thrust equal to drag. Here we may not have a horizontal equation. Like if it is just hovering, we just have thrust equal to weight. Okay, so therefore in a quadrotor you can see that your thrust by weight is equal to 1. Okay, but so this is during hovering, but if you are but during takeoff or while maneuvering it will require more thrust than this. And also there has to be some kind of margin, right? Because when your quadrotor is flying up the air density decreases, or what might happen is that there might be a bit of extra payload in the quadrotor, so usually the thrust is more than the available thrust is more than the weight. Okay, so for quadrotor we have T by W greater than equal to 1. So anybody has any questions? Okay, then I'll move to the next question. So please answer this. Okay, you are right. So the answer is elevator. So we know that the rudder controls the yaw, aileron controls the roll, your elevator controls the pitch or the angle of attack. Okay, and the throttle controls the rate of climb. Rate of climb and you can say velocity. So, hmm, so if we draw the aircraft, okay, so this is the rudder. Then you have wings. So this is your elevator, and this is your aileron. If you look at it from the top, okay, we'll do it later. So your wing, okay, the wing is usually situated close to the CG. Okay, the CG is a little ahead of the wing aerodynamic center. Okay, but the wing is usually close to the CG. So if we place any control surface on the wing, okay, it will have less effect on the longitudinal stability. Okay, if we place any like this aileron, when we tilt it downwards, okay, suppose we tilt the aileron downwards, okay, it will produce, because the airflow will go downward, okay, so it will produce a uh, pitch down moment. Okay, so if your aileron is deflect, if both the ailerons are deflected downwards, then it will produce a pitch down moment, but it will not be very high because this is very close to the CG. So that is why we place a control surface far away from the CG over here. Okay, so when the elevator is deflected downwards, this produces a pitch down moment. Okay, so if it is deflected downwards, the airflow will go down, which will cause a pitch down moment. And similarly, if we deflect it upward, it will airflow will go up, which will cause a pitch up moment. And uh, the pitch up and down moment is directly correlated to the distance of the tail and the CG. So as you can see, so if we would have placed it here, it would not work. So the elevator controls the pitch, and then your rudder, it controls the yaw. Now if I draw the top view, and this is your you can say CG. So if your rudder is deflected this side, then the airflow will be diverted that side, okay, which will cause a this kind of yawing motion. And again, since it is far from the CG, okay, it will cause this yawing motion. If we place the rudder directly over the CG or near the CG, it will not work because the moment will be very low. Okay, so this is the rudder action. And next we have the ailerons. So the ailerons are control surfaces which are placed, okay, on the main wing and a bit far away also. Okay, again for similar reason, if we place the aileron, okay, very close to the CG, since it is close to the CG, it will have lesser effects. Okay, so the ailerons are usually placed farther, like they're placed on the wing, but they're placed far towards the tips. Okay, and the ailerons are usually deflected uh, in a opposite manner. Like if your left one is going down, your right one will go up. Okay, so this will, like, if we deflect it down, then the airflow will go down, and if we deflect the right one up, the airflow will go up. Okay, so this will cause a, okay, wait, airflow is going down, so okay, so this will cause this kind of a rolling motion. Okay, so finally the angle of attack is controlled by the elevator. This is the next question. Yes, so you are right. The lift, all of these factors, they are responsible to generate the lift of the aircraft. So we'll discuss these factors. Okay, so angle of attack, you know that if your wing is like this, okay, and your uh, velocity, okay, so the V infinity is like this, okay, so the air is flowing in this direction, and your wing is like this, then this is your wing, um, this is your mean chord line. So the angle between these two lines is the angle of attack. Okay, so you can think that the angle of attack is how much tilted it is with respect to the velocity. So how much your wing is tilted with respect to the velocity. So of course we know that if the angle of attack increases, the lift of the wing, it increases. Next we have the wing incidence angle. So this is there is like a subtle difference. So wing incidence angle is the angle at which the wing has been attached to the aircraft. So we can attach the wing like this, okay, which is symmetrical, okay, or we can attach it in a tilted manner also, okay, like this, okay. So in this case you have to see that what is the, like there is a difference, okay. So when we talk about angle of attack, we talk about the angle of attack of the aircraft. But since your wing has been attached in this tilted fashion, when the air it reaches the wing, okay, the situation will be like this. There will be an angle between the wing and the airflow. So although the aircraft's angle of attack is zero in this case, although the aircraft's angle of attack is zero, the wing has a local angle of attack. So this will again produce more lift even at zero AOA. So the wing incidence angle, it also affects the lift. And then as you know, like as I've discussed till now, the wing camber, it also affects the lift. If we have a positively cambered wing, then it will generate more lift. So this is another question. So this one is quite simple actually. Okay, so you are right. The induced drag for a aerofoil is zero. Okay, but you must understand that. So like aerofoil is like a 2D wing. Okay, so aerofoil is like a 2D wing. Okay, so this is a imaginary kind of wing. So if we assume a wing of infinite length, then uh, that is a aerofoil. Okay, so and a aerofoil has a zero induced drag, but in the real world we work with 3D wings. Okay, so in case of 3D wing, the the wing is terminated at some point, right? So if we assume this is the aircraft body and this is the wing, so the wing has to end somewhere. Okay, this is not a infinite wing. So what happens is that now if we assume that this is a wing, okay, so below the wing we have high pressure and above the wing we have low pressure, okay. And what happens is that near the edge, okay, near the tip of the wing, this high pressure air, it leaks and comes above the to the upper surface, okay. So at the edge of the wing we have these kinds of vortices, okay, because the high pressure air, it flows from below and comes up, okay. So towards the edge of the wing, the lift is lesser, okay, because of these motions of the air, okay. But in the middle the air flow is like the aerofoil only, so the middle part it produces lift, but towards the edge it decreases. So the in this case the aspect ratio of the wing, it plays a crucial role. So we know that the aspect ratio is b square by s. So your b is the length of the wing, and your S is the surface area. And then we know that the drag can be written as CD naught plus KCL square, okay. And your K is 1 by pi E AR. So you can see that so this is the induced drag. So in case of a aerofoil, it is a imaginary, like infinite imaginary wing, okay. So this has a infinite aspect ratio actually. So when you have infinite aspect ratio, the K is 0, okay. So when K is 0, there is no induced drag. But in case of real 3D wings, we have some kind of aspect ratio which creates the which makes non-zero induced drag, okay. But we can understand that if we create a longer wing, if the aspect ratio is higher, the drag will reduce. So in aircrafts which require very low drag, like in case of gliders and all, the wing is very long, okay, because then the drag is minimized. So this is the next question. Okay, so you are right. The correct answer is A. Um, the altimeter and the pitot tube, they measure the altitude and speed of the aircraft. So uh, how does it work? So as I have discussed previously, when your altitude, when the altitude increases, the pressure decreases. Okay, at least in the troposphere. So as the altitude increases, the pressure decreases. So if we can measure the static pressure of the air, we can compare it, we can fit it to the formulas, and we can get a idea of the altitude. So the altimeter, it works like this. So we measure the static pressure. We fit it to the model. Okay, we fit it to the model to get an estimate of the altitude. Okay. Uh, Now, what is the pitot tube? Pitot tube is a device which measures both the static pressure and the dynamic pressure. So it measures both the pressures, and using the difference between them, it can calculate the velocity. So as you know that the pressure is equal to the static pressure plus the dynamic pressure. So we can find the velocity as, okay, so using this formula we can find it. So the pitot tube, Now, one interesting thing I would like to say is that the altitude measured by the altimeter, you can see that it solely depends on the air pressure. Okay, so this might not be equal to the altitude from the ground. Okay, uh, so usually when planes are flying to airports of different altitudes, they have to calibrate their altimeter with the ATC. So suppose a plane, okay, it takes off from a ground level airport and it lands over here. Okay, it has to land at a airport over here. Okay, so suppose the plane has to take off from here and it has to land at a airport which is on a hill or somewhere. Okay, so the air pressure over here is lesser, right? So your rho is lesser, and wait, not rho, your pressure is low over here compared to this one. So your altimeter will say that the plane has not landed and the plane is like it is still flying at some altitude. Okay, the altimeter will say something like this. So usually what happens is that the plane takes off from here, but then midway it has to communicate with ATC and it has to reset its altimeter. Okay, so that when it comes in for the landing, okay, so when it is trying to land, the altimeter measures the distance, it measures the local altitude, so it measures the altitude from this hilltop, okay, and not from the sea level. So this is a interesting thing I wanted to share. And modern aircraft, okay, they also have other kinds of altimeters. They also have radar altimeters. So radar altimeters, they fire like a radar beam towards the ground and they measure the altitude. So this is useful during takeoff or landing, okay, when precise altitude is required. Okay, this is the last question. Okay, so let us solve this. So the weight of the aircraft is 1000 kg, which we can write it in newtons as this. Okay, 1000 into 9.81. The lift to drag ratio is 15. So now we can find out. So this is the cruise condition. Okay, so we can find out the thrust. Thrust is weight by CL by CD. So this comes out to 1000 into 9.81. by 15. 654 Newton. And to find the power, we know that power is equal to thrust into velocity. So this is 654 into 50, which is 32700 watts. Is 32.7 kilowatt. Okay, then so thank you for coming to today's interactive session. Uh, like we'll meet again next week. Okay, so there is another interactive session in on Tuesday, but I think the same thing will be covered there. So we can meet next week.